I'm going to start sharing my screen. And I reached a executive decision last night. Today we'll be finishing the chapter. Today, I think there's one thing that we need to talk about, which should not take long. And then we'll use the rest of the class to answer any questions that you might have about the activities and the homework. And because we're just finishing up today, I think initially the test was supposed to have been a while ago, but this chapter's taken a little bit longer than I had thought it would. And so I am going to, I think I've got an empty page at the end of these notes. I'm going to say, if it's all right with everybody, I don't think it fully contradicts anything that we've said previously. The test on chapter 9 will be available next week. Monday through Tuesday, Monday from 11 a.m. till Tuesday, 11:59 p.m. The test will be in Blackboard, and don't feel like you have to type everything. If you don't want to type anything, you don't have to. You're going to submit your handwritten work. And if you want to, you can submit all your answers. You don't necessarily have to type anything in Blackboard in the Dropbox. I don't think there was anybody where I couldn't open your entries in the Dropbox. So I don't think that that should be too problematic for anybody, but does that sound reasonable? Initially, I was going to have the quiz over the weekend, but because you're still working on the homework and doing some of that hands-on stuff, I thought I'd leave the weekend go, and I'm going to start that next chapter 10 on Monday, but if there are any last minute questions, we can deal with them before you take the test. Does that sound reasonable to everybody? Okay, great. Then let's go back, and I think we left off on page 19. We're looking at three-dimensional solids, and I'm going to stop sharing for a minute because in that homework, I think I had said that I wanted you folks to
make one, and I forgot to submit mine. Can I email it to you?
Yeah, you can, and send me a picture. I wanted to show you guys what I made. So can you see my little three-dimensional creation that's very carefully made? You can see I used the finest of ingredients. I got toothpicks. Usually if you're using toothpicks, it's easy to use like marshmallows or something in the corner. But my husband and I are trying to steer away from carbs and sugar. And so instead of marshmallows, I've got raisins holding it together. And so I don't want a real simple salad. I want something that's a little bit more involved. As you look at this, I don't know if you can see, if I were to name it and describe it, what I've got in the middle here, if you can see, I've got a cube. And then I put a pyramid off of each face of my cube. And so this figure, which has 6 pyramids on the edges of my cube, actually would have 4 times 6 or 24 faces. And I could count my raisins to see how many vertices I have, and count my toothpicks to see how many edges I have. And I might put that in my description of it. So does this give you guys a little bit of better of idea of, one way you can create that three-dimensional figure? I guess if you wanted to, you could draw a net and cut the net out and tape it together. And you could submit a picture of the solid and this picture of the net. If you want to use something other than toothpicks, you could probably use straws, or there's all sorts of different ways that you can create something. But this was sort of fun to make, and it took me all of about 5-10 minutes because I was just kind of like sticking my toothpicks into my raisins until they held. So better idea on what I'm looking for in terms of a three-dimensional model. If you submitted already and didn't give me a picture of it, it would probably be better for you to email me that picture than it would be. I'm thinking I could make it so that you could do another submission, but I don't know that it allows me to combine the two submissions into a single grade. But general idea of this, okay. Then, now I have all those raisins to snack on during class. Not really. Oh, actually, I want to stop sharing once more. I had also told you that if we were on campus, I would have handed out these relational solids. And these relational solids, I don't know if any of you had the opportunity to work with things like this at all in your mathematical career. What I have right here that I'm holding up, can everybody see? I've got two bases that are triangles, and they're in parallel planes. The lateral faces are all squares. This would be a triangular prism, as opposed to if I hold this one up only has one triangular base, and all of the lateral faces, the other faces that aren't bases, meet at a point, which means it would be a triangular prism, differentiating between a pyramid and a prism. And this box of relational solids has a lot in them. Over here, you can see I've got a hexagonal prism. Over here, I've got a square prism, which would be a cube. I've got a square pyramid. I've got, we'll pull out one more. You see this one, the base is a rectangle. So this would be a rectangular prism. So all sorts of different solids. And I am going to be pulling them up again in a minute. I'm sorry making you guys look at a picture of me, but look at the solid in front of me, not me, to consider, where we're going next, which is Euler's formula. I know this looks like it's pronounced Euler's, but it's pronounced Euler's. It's a German name. It's named after a famous mathematician. And I have to apologize, I don't have quite all of these shapes here, but we'll look at a couple. So I do have a hexagonal prism. And so I'm going to ask you folks in your notes to please mark down as we count, and then look over with me. I'm going to stop sharing. First, we want the number of vertices. And the vertices would be the number of corners. And so as I look at my hexagonal prism, does everybody see on this side I'd have 6 vertices. On this side I'd have 6 vertices. So altogether, this thing would have 12 vertices. Then we're asked to count the number of faces. Number of faces, I have my 2 bases, and then I have going around 6 other faces, the rectangular sides, and so that would give me 8 faces. Can everybody see counting them? And then lastly, the edges. Well, on each face, I'd have 6 edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'd have 6 edges going around in between my lateral faces. So that would total up to 18 edges. And so my hexagonal prism had 12 vertices, 8 faces, and 18 edges. Instead, if I look at my cube, does it help you guys when I hold up the 3-dimensional solid to look at, or no?
Yeah.
Yeah. Okay, then I'm going to look at my cube in terms of vertices, corners. Does everybody see we'd have 1, 2, 3, 4 at the top, 1, 2, 3, 4 at the bottom. So altogether we'd have 8 vertices. In terms of the faces, we'd have 1 on the bottom, 1 on the top, and then going around, I'd have the 4 other sides. So that would give me 1, 2, 3, 4, 5, 6 spaces. And then the edges, I'd have 1, 2, 3, 4 along the top, 5, 6, 7, 8, 4 more at the bottom, and then these 4 along the sides, adding up to 12. So there we had with the cube 8 vertices, 8. No, we didn't have 8. We had 6 faces. I can count. And we had 12 edges. And then the last one that I want to look at that's in this list is the tetrahedron. The tetrahedron is actually your triangular pyramid. It's got 4 faces, tetra being 4. So that's my triangular pyramid. And so if I hold up my triangular pyramid, this one, do you notice I've got that apex, that vertex at the top, and then 3 at the bottom. So that would give me a total of 4 vertices. I have 1, 2, 3, 4 faces. And I have 1, 2, 3, 4, 5, 6 edges. Did everybody see them all as I was counting them?
Mhm.
And so here, I have 4 vertices, I have 4 faces, and I have 6 edges. So now we want to look at those numbers, those columns going across, and see if there's a relationship that holds true with those 3 numbers, those 3 numbers, those 3 numbers. And does anybody notice any? Or did anybody have a chance to read the textbook and find out what Euler's formula says?
Isn't it V plus F equals E minus 2?
V plus F equals E, I believe it's plus 2, right? If I look, 12 plus 8 is equal to 20, which is 18 plus 2. 8 plus 6 is 14, which is 12 plus 2. 4 plus 4 is 8, which would equal 6 plus 2. So the vertices plus the faces is equal to the edges plus 2. And I believe there's some in the homework that asks you to make use of those relationships. If I know the vertices and the faces, how many edges do I have, or some other combination of that information. And so those are my polyhedron. They're 3-dimensional surfaces, and all of the faces are polygons. We also have comparable things, but with, excuse me, I'm tripping over my tongue today, circular sides. And so a cone, I think everybody's seen a 3-dimensional cone. If anybody goes for ice cream, I think, does everybody know that when you get ice cream, the sugar cone is ever so much better than those cardboard other cones? And the sugar cone is actually in a cone shape. And so the base is a curve. We are going to mostly look at ones where they're circles, but they could be ellipses or any other type of curve. So this bottom is my base. The apex is that point at the top. I actually only have 2 surfaces, right? Because I have the base, and then I just have this one single surface that goes around the apex. The altitude is going to be perpendicular to the base through the apex. I guess if it's right, it'll be perpendicular to the base, as opposed to if it's oblique. If this is my base, if it's oblique, it means it's kind of like slanty. In my mind, when I look at that oblique one, it almost makes me think of a witch's hat or something like that. Here, my altitude would be perpendicular to not necessarily the base, but my altitude would be perpendicular to that plane that contains the base. And so in my mind, a cone is very similar to a pyramid, that it comes to a point, as opposed to, last page, a cylinder. And a cylinder is like a can. It's got two bases that will be congruent curves. And it only has one lateral surface. But they remind me of a can. Has anybody in their food career ever taken a label, which would be like the equivalent of that lateral surface, off a can, which would be my cylinder? And if you think of taking the top off a can, a bottom off a can, and the label off a can, wouldn't the net look something like that, where the top and bottom would be circles? And then if you peel, has anybody peeled the label off a can? When you peel the label off a can, isn't it kind of like a great big rectangle? And what we're going to find out to be interesting later is this width of the rectangle. Wouldn't that have to be equal to the circumference, the difference around my circle? How fun is that? So now I'm going to shut up, because that was what we didn't get to on Wednesday with the notes, and that's the last of the notes that I had planned to give this chapter. I apologize for not having class time in which to work on the activities, but we have the rest of today, which gives us a half an hour to deal with questions that you might have on any of the activities or on any of the homework problems. So, or on anything that we did in the notes. Any questions on anything, folks? Does anybody want to look at any of those homework problems or any of those activities?
Can you go over number 8 on page 440?
Sure. I have to apologize. It's going to just take me a minute to get to that virtual textbook. I did not have an opportunity to open it before. And is it worth the effort to open the virtual textbook? Does it help you guys to see the question in the book, or can I just read it from the book? If it lets me open the virtual book, here we go. Maybe it would have been quicker to just read it from the book. Yeah, it's still not up there. It's coming, it's coming, it's coming. There we go. See how long this takes. Page, what was the page number?
440. Well, it's on 441, but.
Question number 8.
Yeah.
Okay. Well, we'll give that time to work its way out. Question number 8 says, use a compass or carefully trace two intersecting circles, determine a line as shown in the next column of the diagram. Draw 3 circles where each circle intersects the other 2 circles, as in the example shown at the right. Then draw the 3 lines determined by each pair of intersecting circles. What conclusion is suggested by your drawing? So what they're asking you to do is they're asking you to draw 3 circles. Can be the same size, can be different size, just 3 circles that intersect like the ones in the picture. So, okay, those 2 intersect. And then I want a 3rd circle here. Now, if I look at the first 2 circles, they're talking about the line that's formed. Let me undo that. They're talking about the line that's formed where the 2 circles intersect to the other point of intersection. So there's one line. Then I'll make the next one for this circle up. This circle. This circle intersecting here. And that's a little off, I apologize. And then the other line would be where these 2 circles intersect. And what do you notice about those 3 lines? The blue line, the green line, and the black line? Do you notice anything about them?
They all intersect at the same point.
Beautiful. That's it. They're just asking you to draw the picture and notice that those lines all intersect at the same point. If you want to be fancy pants, we had a definition for lines that all intersect at the same point. I think we call them concurrent. So we could say the lines all intersect at the same point. They're concurrent. But again, I'm looking for this picture. And please notice that I took the time to make real good circles, because if I did it with circles like that, it wouldn't happen. So please make an accurate picture. All right. Was it easier than you made it out to be?
Yes, much easier.
Yeah, but again, make sure your circles are really, really round and make sure your lines are really, really straight. Anybody want to look at any other questions from the textbook?
Can we do number 20 on page 461?
Sure. Let's see if I actually got the book. Oh, I do. So page 461. Question number 20 says, for each regular engon shown, give the measures of the interior, exterior, and central angles. Okay, so let me grab, well, I don't want to give you a poll. I want to grab a pen. And does it matter to you whether we do A or B together?
Doesn't matter.
Okay, let's do B. B, how many sides does that figure have?
6.
6, and is 6. Now, do you remember the exterior angles? We said always add it to 360. And if I've got 6 sides, I have 6 angles. And so when I go and divide that out, that would give me that the exterior angle is 60 degrees. Likewise, the central angle, that angle in the center all the way around adds up to 360 degrees. And if I have 6 sides, wouldn't I have 6 of those central angles? So 360 divided by 6 tells me that each central angle is 60 degrees. Now for the interior angle, I have 2 choices depending on how hard you want to work. The formula for the interior angle, it said that the sum was equal to 180 times the number of sides minus 2. And then for each one, we divide by the number of angles. So that would be 180 times 6 minus 2 is 4. And we'd have to take that and divide by 6. Now, because I'm trying to do this arithmetic in my head, I'm going to say I know that 6 goes into 18 3 times. So 6 goes into 180 30 times. And that gives me 120. And you notice doing it that way, I don't have to do the multiplication 180 times 4 and then the long division dividing by 6. And so each interior angle is 120 degrees. In my mind, though, that's the hard way. The easy way, this is a straight line, isn't it? If this exterior angle is 60 degrees, and that forms a straight line, to find the interior angle, because that's a straight line, don't those 2 guys have to add up to 180? Don't they have to be supplementary? So not the interior, but the interior, wouldn't it be that 180 minus 60 or 120, which takes me to the same answer as the other formula? Better?
Yes, thank you.
You're welcome. Can I erase?
Yep.
Okay. Anybody want to look at anything else from the textbook? Or does anybody want to look at anything from the chapter 9 activities? Do you folks have all of this work done and you're really confident in what you did and you have no questions? I'm impressed.
I did pretty much all of it, went over it with the tutor, so I feel kind of confident.
Okay, all right. And confident enough that you could revisit those questions on your own without a tutor and get them. That's what we're looking for. How about anybody else? Anybody else want to look at any other homework questions? I usually in on-campus classes probably spend as much time helping people with the homework and the activities as I do with going over the notes. So don't be shy if you have a question. Yep. 442, question number 24. Is that what I heard?
Yeah.
Okay. So 442, question number 24. Oh, I love this question. What we've got here is this picture. And as I look at this picture, what I know is that PQ is parallel to AB. And I also know that RQ is parallel to AC. And I have to find the measures of all of the angles 1 through 8. And I'm going to tell you, I'm making this bigger so I can write all over it. When I do these, I don't always do them in the order that's shown. So first of all, as I look at this picture, I want to look at PQ being parallel to AB. And if PQ is parallel to AB, can I look at this here as a transversal? And so if this is my transversal, do you see how angle 4 would correspond to this angle over here? That's 40 degrees. And so this angle would be 40 degrees. Now I'm going to look at my triangle. And do you remember that the sum of the angles in a triangle is 180? So if I take that 75 and add that 40, I get 115. And so if I take 180 minus that 115, I get that angle 3 over here is 65 degrees from the triangle. Now, if that angle is 65 degrees, this can be my transversal. I'm looking yellow might be a bad choice of color. Can you guys see the yellow or no?
Yeah.
And if this angle is 65 degrees, wouldn't this angle be 65 degrees? And wouldn't it be the fact that 65 and this angle have to be supplementary because they form a straight line? And so if I take 180 minus 65, that gives me that other angle is that 115. And now, let's see. Oh, I just saw another one that I missed before. We use that color, dark green. If this is parallel to this, if you tilt your head a little bit and use this as a transversal, wouldn't this angle have to be equal to this angle? Wouldn't those two be corresponding angles? So angle 6 would also be 75 degrees. And if I look at this figure in the middle, if all those are parallel lines, isn't that a parallelogram? And so if this is 115, isn't this one 115? And if this is 65, isn't this one 65? And I guess lastly, to get angle 8, if I look at this line being parallel to this line, I see a Z there. Would an angle 5 and angle 8 be alternate interior angles? So that angle would also be 65 degrees. Or I could use that triangle adds up to 180. And there's all sorts of other ways of getting that. But when I do these types of questions, I go through and try to find all of the angles using my parallel lines and my triangles and the like. Then I fill in the blank with the answers. Does that help?
Thank you.
You're welcome. Do you guys need me to leave this scribbled on picture up here, or do y'all have it? Can I clear it? Anything else from the homework that anybody is wondering about? That question was kind of similar to, did I give you guys 15? It's along the same lines. Expect to be able to do that type of work on the test. Any others anybody's wondering about?
Sorry, need level 15 as well.
Okay, 15? Sure. Though this time I'm going to ask you to help me a little bit. As I look at 15, let's start over here. If this angle is 60 degrees, if these are straight lines, what would angle 5 have to be?
60,
Beautiful. And if this is a straight line, what would angle 1 have to be?
120,
120. And if that's 120, what's angle 4?
120,
And if these are parallel lines, you see I've got, well, it's sort of backwards, but you see I've got that Z kind of thing going on here, which gives me alternate interior angles. So angle 8 would also have to be 60. But all those other angles are kind of chopped up a little bit. But if this angle is 70 and these are straight lines, what can you tell me about angle 9?
70,
Beautiful. And so if this is 60 and this is 70, 60 and 70 add up to 130. How big would angle 10 have to be? If-
150,
Let's see, these three angles, if they make a straight line, wouldn't those three angles have to add up to 180? And so did you say 150 or did you say 50?
oh, yeah, it'd be 50, sorry. I didn't,
I know how you're thinking because my mind and my mouth work that way sometimes too. But are you all right? It's more likely to be 50 than 150.
mm-hmm,
Okay, now if this is a straight lines, then wouldn't this one also be 50? And wouldn't this vertical angle also be 60? And am I being childish changing colors, or does just changing colors help?
It definitely helps because you can see the separation.
Okay, then use colored pencils when you do these. Do you see the Z here?
yeah,
So if angle 10 is 50, how big is angle 6?
50,
And if angle 6 is 50, how big is angle 3?
50,
And if this is a straight line, how big is angle 2?
130,
Beautiful. And if that's 130, how big is angle 7?
130,
And you notice, if I try to get the angles in order, if I try to go, what's 1, what's 2, what's 3, what's 4, it would have blown my mind. But you see how I can kind of just go around the figures and use what I know to find all of the angles, and then I'll fill in my answers. But with something like this, I don't want just a list of the angles. I want a little bit of work, a little bit of explanation. You know, you draw the diagram, annotate what you did. Okay,
okay, what about the 14?
14.
Mhm.
Oh, the one that I think, should I do the one that I think is hardest in 14?
Sure.
Well, let's do one of the easy ones and then one of the hard ones. I think 7 o'clock is easy because 7 o'clock, if I look at my clock, it should be 7, 8. It should be 10 and 11. I'm just messing with numbers today. All the way around is 360 degrees. And if I divide it by 12 for each number, does everybody see that every time I move over a whole space, it's 30 degrees. Every hour it moves 30 degrees. At 7 o'clock, the minute hand would be exactly at 12. The hour hand would be exactly at 7. So I'm moving 1, 2, 3, 4, 5 times 30 or 150 degrees. Is that one straightforward enough? Where it gets a little dicey is if I look at 1020. And at 1020, well, at 20, my minute hand would be exactly at 4. But at 1020, my hour hand would not be exactly at 10, would it? It would be moved, somewhere in between 10 and 11, wouldn't it? So we've kind of sort of got to figure out what that angle is there. Because otherwise, they would be directly across from each other, which is 180 degrees, but they're not, because isn't my hour hand partway in between? So how far between would that be? Well, over the course of a full hour, over the course of 60 minutes, it moves the hour hand in 60 minutes, moves 30 degrees. So what could we say? We could say every 1 minute it would move a half a degree. So in 20 minutes, wouldn't it move 10 degrees? And so this angle over here would be 10 degrees. With me so far?
Yes.
And so this would be a straight line. But if I'm going 10 degrees off, what would this angle be? Straight line would be 180. And if I'm taking away 10 degrees,
And
how
seven.
many? 170. How cool is that? You have to take under consideration that at 10:20, your hour hand isn't pointing directly at 10 anymore. It's moved over a little bit. So in that same way, in that same way, at 4:30, the hour hand is not exactly at 4. Wouldn't it be like halfway between the 4 and the 5? So keep that in mind as you look at those. Little bit more involved than you would think.
Thank you.
You're welcome. Any other questions on any of the other homework? Or the activities? How are you guys doing with those activities? No other questions? If not, I'm going to stop sharing. And I guess we'll stop recording.